Can you hear me okay? I see anybody in the other room. It looks like there's 2 people here out of our 45 employees. I'm not sure when we come together. Remember, I take attendance. Anything going on today? Like I think we're fair or something. I'll be waiting. Just to recap, I will be at a business meeting in Washington next Wednesday, down on Tuesday, right back on Thursday. So we will be losing 1 day, and that's Tuesday next week. However, I have arranged for the TAs to come in and give you an early tutorial. And did you all receive the remote desktop document on email? You may not receive it. You will need to bring your laptop. And you might have to check to see if the remote desktop is working okay. Sign in on remote teaching servers with your account number and password, which I assume you also all have at this point.
Juicy.
I'm going to have to get password. Steve Nicholas to make sure he sends it. I have the impression he was all done with it, I'm not sure. And you all need those account numbers and IDs and passwords. Now, TAs, when they're giving tutorials, they know how to use the tools, so they go and they click on a menu and they say, click on this menu item, and then they give you a small pause and then they just go on. So if you're still struggling to try to find where the stupid menu item is and they move on, you'll fall behind. So you need to be very vocal and say, wait, scream wait, if they're getting ahead of you. Back up! I'm lost. Now there are 2 TAs, I'm hoping one of them will be up there operating, and another one might circulate around and help you out if you get lost. There will be a document that comes out. I'm trying to find the most up-to-date one on how to use Cadence. So the first thing is get logged in a teaching server. And mind you, teaching servers, Cadence. It's time sharing all over the place, right? I put up with it when I was an undergraduate. Stunk. You didn't understand. I mean, trying to move, some little piece of artwork around, move the cursor or something, it just doesn't. You're on time sharing. So the idea is that we have set aside some dedicated workstations, Dell workstations over in CII 6118. I believe there's 6 of them at this point. You can come in any time during the week, and there should be a few of them around. I'm getting ready to buy some new super duper ones for my graduate workstation booth down the hall. And as I buy these new 22 gigabyte machines, I'll pick some of the 16 gigabytes over to you guys, which will be more than enough for the teaching kind of thing. Anyway. So again, that will be next Tuesday. All right. So we've been talking about the field effect transistor. Without getting into all the 3D part of the drawing, it's basically a thin oxide with a gate material, and there'll be some openings in the thin oxide. Contacts, we use the gate material we call shadow mask, and iron plant, which is like either phosphorus or arsenic boron, and this provides a region in here which is undoped, except for its opening is inserted during the growth of the silicon. You can introduce into growing the cell. And so the one we were starting with was the NFET, which is end of these regions here. And then in this region is grown as ketones. And then we have contacts, we said have to be ohmic. And then we have field oxide, which provides kind of a device-to-device isolation. Actually, I've drawn this in a very skewed dimension, because usually this surface is way down here someplace, unless this is something called SOI. SOI is another brand of CMOS in which an oxide is down here, and we bind a ketone wafer, say, onto that oxide, there's another holding. And it provides some isolation to the substrate, which has pluses and minuses, one of which is some of the device capacities are reduced by doing SOI, because this is all oxide down below this point here, so there's nothing to grab onto. But I'm drawing it in kind of a distorted scale. This would be very far down to non-SOI. And we said, well, we'll ground this for the sake of discussion. And then we would apply the two voltages, which are positive, and we would ground this guy here. So this guy is essentially connected to that. And this has got a bias on it called V gate to substrate. It's basically from here down to the substrate. But of course the substrate is in this case at the ground voltage, so it's the same as the substrate voltage. And then we have another battery over here, which is VDS, because in this configuration, this is the source of electrons. When this is positive, it exceeds the threshold voltage, and electrons begin to migrate under the plate, essentially passive plate formed by the heat and oxide that's under this stuff here. So when we draw this, if we look at it as, something you might see in cadence, it would be basically a long gate type of a structure. We would have our field oxide defined source and drain with their respective contacts, the various source and drains. And this is kind of a crude picture of what we would expect to see moving down onto the cadence artwork we have in front. But there are actually other layers in there. There's little extra layers for near the channel, and when we get into all of that at this point, we will recognize it when we see it. This dimension here, we said, is the channel length, L. This is the z-axis. This is z equals 0, this would be z equals L over here. So this dimension on your artwork will be the length of the channel. And then this dimension, the other direction here, is on the edges of the source of drain implant, the width, so-called, of the channel. And as a designer, I'm sorry to say that's all you get to fiddle with, is the width and the length. And usually the length, to get the best packing density, is fixed to the minimum feature size. So that means there's really only one thing you have to fiddle with, and that's W. So the good news is you only have to worry about W. The bad news is you have to worry about W. And it's a little bit complicated and involves a number of features, which I'll get into in today's lecture. But when we build the structure, we get our classic IDS versus VDS plot, which in a typical applied voltage for the VGS, as long as it's bigger than the threshold, will give us a curve that looks something like this. It may not look exactly like that in transistors. First of all, this tends to tilt up a little bit, and it may actually be kind of rounded. So it's sometimes hard to tell where saturation begins and where it ends. simplistic case, and usually where the definition lies, is to pick the peak of the parabolic section of the curve and put to output this with fixed EPS greater than the threshold. And then this is the area which we call active. And this is the area which we have called saturation. We also showed last time that there's a locus of points for this transition between active and saturation. And as we begin to go down in voltage, this point, which is at VGS, VDS equals VGS minus the threshold. As we get down to the point where VGS equals V threshold, this point is down here at the origin. And it will just go flat. Now that's not quite exactly correct either. It's a simplistic model that will be suitable for designing circuits, diverse wars and things like that out of it. But when we get down to this near threshold activity, which we have been calling cutoff. Cutoff is a special case of saturation that we're viewing it here, where this point is just going all the way down to the origin. That actually there's leakage. And leakage can be partially due to the diodes not completely blocking the current. There's some leakage current in the diode. And there are other kinds of effects, particularly if you don't scale as well. And this dimension here, L, is very small, but this dimension is not. So you wind up with kind of like almost, a big hunk of material, any part of which could be still having some residual current flowing, what amounts to the channel. So the proper scaling device, if you want to make this small, you have to make these dimensions smaller too, which can be a bit of an art. But you also want the opens to become what we call electrically active, which means you have to go to a site in the silicon lattice, expel a silicon atom that was there and push it someplace else. And then you need that process is called thermal annealing. It's one thing to whack this thing with an ion planer and push in these dopants, but they got to go to the right place. That's done at high temperature. And it's one of the high temperature steps that you do with the CMOS processing. So up in this area here, which is the active region, we derived the IDS, which was being equal to beta for the FET, and it would then have VGS minus the threshold times VDS minus VDS squared 2. And where the beta is equal to mu Cox and with the length. Which says if we want to make the current go up, or have more current to work with, then the only knob we have as designers to work with is the width to length ratio. So if we make the thing wider, we will have more current to work with. And if we're trying to drive a load like a capacitor, then we're going to want the current. Unfortunately, the leakage will also go up, but we're not treating that very comfortably here for this analysis. And it's actually kind of hard to treat properly. You have to, in some cases, resort to numerical analysis methods to model it correctly down there. But there are some formulas that will tell you what's going on. And that's a big battle with the current modern era. It's how to depends that the leakage will be a big problem. But you can make the width length smaller, and now you have less current. So that's a way to sort of save energy. And it's also true that the current is bigger if we have more voltages. So that's another way that we can make things have more current. When we need more current, sometimes we have to charge other parasitic capacitors like wire. They have some capacitance back to the dominant feature. And frequently dominates microcomputer cycle time. It's just wire. Now when we get up here, we we go through our little derivative process, evaluate basically at the peak, and then that tells us what we call stat, which again is this beta n. And now we have the VGS minus the threshold all squared. And so if we're fixing this, and of course this is fixed, we have a fixed IDS sat up here. And again, if you want more of that current, you can make the link ratio bigger, or possibly work with larger voltages. The other side of this is making the voltages go down. And if you make them go down, then again the current goes lower, and maybe the power will be reduced. But if it gets too close to the threshold, then the whole model starts to break down. There's a special area of CMOS design called sub-threshold design, where you actually try to work on this little crack, maybe for your wristwatch or something you want to work for like 6 years without failing or something like that on a single battery charge. But you'll never get any speed that way. Well, your wristwatch doesn't have to be fast. And part of it has to do with charging and discharging mechanism that goes on in computers, charging wires, discharging them, and we need more current to charge and discharge faster. So, wanting performance, generally these things tend to be fairly big. The other thing is it's kind of hard to make the threshold go down. By processing techniques is not something you can do anything about as a designer, but you need to keep one eyeball watching IEEE transactions to what's going on in the field, and new way of structuring the ET go down, and make all the voltages go down. Then of course your current's going down. And is that good or is that bad? If something's portable, it's good. If something just wants performance, it's not good. So, that pretty much is the whole story. The other thing is this here, this transition, if you will, IDS transition, satisfies this law that we have the beta n times, this had a half, sorry, mistake. This transaction here is a VDS squared. Over 2. Okay, so this is a nice little plot, and we have this formula too. But we haven't built a circuit yet. We have the device. By the way, the symbol port we tried last time that most reflects the physics of the device is this tells us it's an N channel. I'll put an arrow in here. We're injecting electrons on the channel side of the gate. And for the way I've organized this here, I'm connecting it directly to ground. Last time we put a battery on it and played with voltages with VGS and VDS. It's not a circuit, it just has battery. Let's begin to look at how we would take a circuit out of this, but might do something useful, because all we would be following here is IDS going through a transistor. You would need a sensor to be able to tell what IDS is. When we try to build a circuit, we don't want to have to go and measure magnetic field or something like this wire. And so we usually have one other component, which is some kind of a pull-up device. And I'm just going to use a resistor here, because it kind of makes it look a little bit like an amplifier, but it's not. I'm trying to show that it's pretty nonlinear, so you probably would want to amplify this. And this is our VDS. And we have our VGS over here. This will be fed in with some kind of source. And input into the thing, so I'll call it VN. VGS. And I'm sorry, this is not VDS. This is a power supply. It says V. VDS is actually the voltage from drain to source. That's here. Okay, so this is just some power supply voltage. And I'm using what we call pull-up resistor. I have some kind of extra pull-up and showing up to that resistor. And now we'll look at this voltage VDS as a function of the in. It's a little different from what we were doing before. And it brings it closer to being what we call a circuit. Now this part of the circuit back here, we recognize that as having a formula for it. And by the way, there's only one, if we say there's no current going out here on this voltage, let's use a high impedance scope to look at it, a high impedance voltmeter to look at it. All the current that flows through here, which is IDS, is also flowing through here. But for the moment, that's the way we're going to look at it for DC biasing purposes. In fact, let me call this VDD, or power supply. This part of the circuit then actually is describable as a load line equation. It's VDD minus VDS, which is also the out, divided by the resistance. So it's this voltage minus that voltage divided by the resistance is IDS. It's a linear equation. This guy over here is very nonlinear. So we're trying to solve a nonlinear equation with a linear equation. So this guy over here is IDS equals some nonlinear function of VDS, okay, which is also a function of VGS as controlling the signal. But fixing VGS for a moment, we want to simultaneously satisfy two equations. We want to satisfy IDS equals VDD minus VDS divided by R. And we also wish to simultaneously satisfy IDS equals this nonlinear function. I'll write it out VDS and also VGS. But that's fixed for the argument. And the way to do that is to put them simultaneously onto the plot. One way to do it is to put them simultaneously onto the plot. So I'm going to do this on the IDS versus VDS plane. The load line equation is just a straight line like this, which intercepts at the point where the current is to be zero at VDD. We want to simultaneously satisfy this equation. By the way, the slope of this is 1 over R. And we want to simultaneously satisfy the nonlinear equation for the transistor, which looks something like this. Or like this, it's cut off, or maybe up here. And of course, I told you before, the spacing between these curves is getting bigger as we increase VGS. It goes up quite dramatically. So we finally get up to this area here. These curves are way up here, so because they pack together very tightly at the end of this extreme. Down here, they're sort of a little bit more spread out, and they get a little tighter over here. Now, for part of this time, we would be above on this characteristic here, the sigma subtype, which is there, would be on the saturation part and would be higher than VDS equals V threshold. That's our VGS minus V threshold. That's the voltage here, and that's the transition point. And these are going up like this. When the transition to saturation is going up on that quadratic curve. And here's a point where the transition occurs there, but there's no point where the transition is on the other side of the line. When we are intercepting, and the interesting thing about this, as we increase VGS, we come out first on the saturation part. We come out a cutoff special case saturation, so the first places we'll hit are on these, and then after all, we're going to go on to the active region over here. And they're still in the active region, but they start to squash together up here. But they're also approaching zero in that direction. So we can actually sketch a picture of what's going on here. And something that is a very valuable plot. You want to pay attention here. This is called a voltage transfer characteristic. Or VTC. And what it is a plot of the output of the circuit VO, which we said is for the VDS for this problem, and the VIN. V out versus V in. And the V in is VGS. So it's a voltage-to-voltage transfer characteristic. When the applied voltage VGS is less than the threshold voltage, well, we're in cutoff. When we're in cutoff, there's no current flowing at all, and no voltage drop across the resistor. And nothing's going this way by assumption. So we get VDD as the output. And it happens all the way up to the point where the input is the threshold voltage, the threshold. So it's absolutely flat. And it's equal to VDD at that point. Right? So it's VDD. Then we're going into the so-called saturation domain. And the intercept point is going up, is increasing VGS up on the curve, so I guess it's going up, but the simultaneous solution of these two is also causing the VDS to go down. So obviously, as the current flows greater to the resistor, more and more the voltage VDD is going to drop across the resistor, the less it costs across the transistor. And so that's going down. So VDS is going down as we increase VGS. And it's fairly clear as we look at it later, it will be quadratic. Now, when we get to the point where one of these curves actually passes directly through the point at which the transition is occurring, is a case where this VDS, VGS minus 3V threshold is right at the point where we pass through the characteristic of the transition between saturation and active. The special condition that applies is that VDS is equal to VGS minus the threshold voltage. Now, this part of the curve here was for cutoff. This right, cut. This part of the curve here was sat. And then we hit a point where there's a connection here between VGS, which is the input, and VDS, which is the output. And it's on a straight line. Slope 1. So this equation is VDS, or V out, that's VGS, threshold, should be in, that's the threshold. And it passes right through this exact point where the threshold is. So this transition point is on that straight line someplace. When we come out the other side, we are in the active region. Now, one of the things we said is that as we come through the active region, these are all active curves up in here. Initially, you might see a fairly rapid drop in voltage due to the larger and larger spacings. But we get squashed in over here. But also, VS, which is the out, is approaching zero. We get a rather large drop initially, and then it just never quite get down to zero. But that's the problem. It's a problem for this particular way of forming a repeat or an inverter. The idea behind the inverter is we put in no voltage, this cuts off, the voltage rises on the output, the power supply, and you get one at the output because zero at the input. Put something on here, turn it on, when it starts flowing, this voltage now is dropping away from high voltage and it's lower. So a high in results in a low out. And that's why this is kind of like a negatively sloped characteristic. High input results in a low output, low input results in a high output. It's a kind of an inverter. Is it a good inverter? Well, let me explain why the voltage transfer characteristic is important. Voltage transfer characteristic is important because it provides noise immunity. Now, it may not be terribly obvious yet, but sort of a little obvious that, when we're changing from high to low on the transistor, we're pushing current here. Some of it in the real world actually trickles out to wire capacitance and maybe other devices that might be out there because they all present large amounts of gate capacitance. We have to charge all of that, but that's neither here nor there. The point being that during that time, a lot of current is flowing from the power supply into whatever is over here. As that surges in, there are inductors in this path. In any real circuit board or any real chip, wire not only has capacitance, it has inductance. And as we subtly surge the current IDS, we drop voltage across this inductor. Okay? And it drops absorbs some of the VDD. And so the signal that we actually are working with at the transistor is bouncing every time we have a transition from non-conduction to conduction. Now, the VDD is applied, and we have lots of other transistors around that may be switching from on to off. And so we're not just seeing one of these, we're seeing the amalgam of all of the other switching events on the chip. All and due to the inductances in all these paths, we begin to get a lot of noise in the power supply, which can actually leak then onto some of the signals. So what we need is a laundry, something will clean all this trash off of our signals. The ideal voltage transfer characteristic would look like what we just got. The ideal would be something like the following. Here's your V in, and here's your V out. What we really would like is something like this. This is VED here, and this is VED over 2. And this is 0. And this is VED here. Okay, that's what we really like. Why do we like it? If the input has a signal, which I'll now do a time diagram like this. Here's our input signal at the end. And it has some noise on it due to switching events in the system. They all play up here. And the output is still VDD. So I make a plot this way of the output voltage. It's just going to be nice and smooth. It might be a little ripple here. It'll be greatly reduced. So it's a laundry effect. Noise on the input gets scraped off by this nice flat pedestal here. Okay? And similarly, if you go and you get on this side over here, and we then encounter some other noise, this would be held to be down in here. Again, we're going to get 0 out, and maybe a little bit of buzz, but not a lot. Everybody see that? I can describe it again. Basically what it's doing is cleaning up the signal. This is one of the most essential things that real logic has to do. It has to clean the input signal. With a real headache if you're doing something with justice injunctions, as we heard today, and that they don't have these kinds of particular characteristics. We can't play with voltage transfer characteristics, and we have to be really, really careful about noise in the system. But you're in a system with 50 billion other transistors. That's 50 billion with a B. And they all decide to jump up and down at the same time. It's like having a bunch of American Indian tom-toms, all banging on the tom-toms at the same time. And it's really hard to see to hear the signal. Okay? So that's why we have to train every gate that we do to be noise cleansing. You got to make a laundry out of it. And that is a constraint that's going to turn out on what we can do with the length ratio. So let's see if we can get a better picture of what these different sections are here, because this is harder than a square characteristic. And in particular, it's very soft over here. So we're not getting much of noise immunity there, it's still coming down. Get some noise immunity below a threshold voltage, but then again, it's tough to get down in there. And this thing is rolling off and it's not nice and sharp, like this one is. Now let's make a couple of observations while we're working with this. The rate at which we move along this curve, say in saturation, depends on how far apart these curves spread. Now, if they spread a lot, we'll get VGS and we'll quickly move over here. So if we have a large beta on the transistor, what will happen is that the characteristic will begin to move towards the left. So here's our picture for the voltage transfer characteristic. And if we increase beta, it goes over here. Okay, so it gets sharper, my feeling. Then it goes into this sort of soft decline after that. And this is the threshold voltage. And that's really the problem, is that, well, we can probably even make this is increasing beta. Well, it's getting sharper, it's also moving sideways over the threshold. For most logics, the threshold is a small fraction of VT, maybe 2/10. Modern here, like as high as 3/10. If we get any closer than that, you can see that we start having problems with noise immunity. This is another problem with shrinkage. And so increasing beta will do that. The other thing is that if we make the R bigger, this curve that we have is going to go this way, 1 over R. And once again, we'll move rather quickly through the curves of the device. And so it's actually increasing beta or increasing R. We'll do the same thing. We'll kind of move it this way and make it sharper, but it's now hugging off to the side, and DVD over 2 will be over here someplace. So while we might get some noise immunity that's fairly big over here, this is noise immunity that would have to be only below VT. Most of our logic signals might actually be bigger than VT, especially when the noise is swinging there, it might be over VT and cause false switching. And of course, the other way is if we decrease beta, maybe I should do a different color. If we decrease beta, the thing will go the other way. It'll never look very good over here. So this is decreasing beta. Or R, that matters, go this way. And never do we get right in the middle with a nice sharp threshold. And we're never going to get perfection, but we certainly would opt to want to have something better than that. But in the course of trying to justify what we would do to get that to happen, we're going to do a little bit of manipulation. So maybe we might like to get the curve, equation for the curve in some of these places. Like, how about that? Get the curve for that. And that amounts to doing a simultaneous equation solution. So saturation part of VTC. Good resistor pull. And IDS, which is the load line, will be this. And that's our output voltage. But it also is going to be equal to the saturation current at the SAT. And that's Vn. And we can rearrange this equation, multiply across by R, and then, flip, say, VDD to the other side, and change signs. When we do, we get V out, which is equal to VDS, is equal to VDD. As the things move on the other side, and we'll change sign, all equation, minus R beta N over 2 times VDS minus V threshold squared, and we just said that was Vn. So fully plugging V in and V out into the equation, we actually now have captured that part of the curve for saturation, which hasn't turned out to be too hard at all, and this will be the top. So here we now have V in. This now equation, V in versus V out. Those box now. And that's basically VTC. This part of the curve. You can see it's a parabola, which will reach VDD. Right, yeah, right at this particular point where Vn is equal to the threshold. And then it's going to come down, and this is a parabolic drop. And then there will be this point at which it hits the Vn of the out equals Vn minus the threshold, which is this linear equation that passes through the threshold. And then we go into a different equation. So we now have captured this part. This is the cutoff part. That's basically constant. Then we have the saturation part. And then what we want to do is to go and get the active part. We can even try to find out what these two voltages are here. Where is that transition point? So let's look at the SAT axis voltage transition. Okay, and so this is happening right when we have VDS equals VDS watt, which is this special thing that is equal to VDS watt, known as the threshold. And so, if we want to do this as a function of VDS naught, VDS equals V, this is output, VDS naught equals VDS naught minus the threshold. We will set up the straight line equation. And that's equal to IDS naught, the transition. Now we can put everything in terms of VDS naught. So we did that before. And then solve the equation. And we're actually going to find the voltage where this occurs. This transition is occurring between action and saturation on the voltage transfer characteristic. So this is where you kind of get into what might the first homework look like. Yeah.
This is I what? I.
This is the IDS. This is VDD. Incorrect. Your name is. You caught something. Your name? Your name.
Oh, you
Y.
M-G.
N-G?
A-N-G.
Oh, A-N-G. Yang
Yeah, Y-A-N-G.
and last name?
A-N-G.
Yang Wayne.
Yeah.
I love that. Okay. You just got a brownie point because you caught me doing a ooh. That means you're awake. That's what I want everybody in here to do. Be awake. Follow what I'm doing. If you find an error, that means you're awake. You're paying attention. It's going into your brain. You're understanding. And I want that. Okay? Every once in a while, I'm going to make a boo-boo on purpose. I think it was an accident. Anyway, we can now rearrange this equation and make it look like a classic draft equation. This part over here, move all this other stuff on the side. And, okay, so this is rearranging this equation, and this is the VDS with the zero. And the VDS with the zero would be out. This is the VDS zero would be out. Okay. We can solve it. Classic quadratic equation. Anybody remember how to solve a quadratic equation? Somebody wants a brownie point. Oh, whoop, okay.
Negative b plus or minus square root of b squared minus 4ac all over 2a.
Excellent. And your name is?
Alexander Peterson.
So somebody picked up another brownie point. Last participation. I asked a question, you answered it. All right. Yeah, so this is an easy thing to solve. And that means A, in this case, is R beta n over 2. B is equal to 1. C is equal to minus 1b. Just plug it all into that stuff. And it says B out at the transition point between saturation and active. And the VTC is minus 1 plus or minus square root of 1 plus, and there's a 1 over 2 in this thing, so 1 over 2 R beta n VDD. And down the bottom is R beta n. The 2 is going to take care of this beta. What do I do? Yeah, A is got a 1 over 2 there. And that cancels this 2. So that's it. That's the answer. Now, that is also equal to VGS naught minus V threshold, which equals V in at this little transition position minus V threshold. So we now have an equation for V out. There's a little bit of a sign ambiguity here. And the question is, which way should it go? Well, if this is negative and that's negative, we're going to have a negative voltage. Not going to happen. We don't have any negative voltages to sustain that. So this better be positive up here, and it's kind of safe with it all the way down. But we can also now rearrange this equation here to get V in, which is on that straight line. So we have an equation for V out, which is this one here. And V in will be just V threshold plus that, so V in equals V threshold minus 1 over R beta n plus square root of 1 over R beta n squared plus V over beta n R over 2. And that should write that out a little bit more clearly. V in at the transition point, the threshold plus happens to be minus of R beta N plus this third. Plus BDD over beta N R over 2. Let's get that. So 2 goes out. Okay? So we wait. Any, what do you not understand? So, again, if we look at increasing betas that are in the denominators, so everything is going to kind of collapse towards the threshold voltage, make beta impact R big, well, this is just going to go away, and just the transition point is just going to collapse over towards the threshold. If we have a small beta R, and we make 2 beta R BDD equal to X, and say that the beta R is very big, very small, so this is much less than 1. You can actually expand some of these formulas, and 1 plus X to the 1/2 power is equal to 1 plus 1/2 X plus a bunch of other terms that we'll throw out because X is small. And in that case, Vn equals V threshold, and we can just replace everything by the linear terms, which makes a minus 1 over beta N R plus, we get a plus sign, 1 over beta N R times, and then we get this simple approximation, which is 1 plus beta R, beta N R, and BD. Which in fact then is approximately V threshold plus VDD. Okay. And so the picture that we get in that situation is, here's our V out, here's our V in, the voltage transfer characteristic. Here's VDD. Here's threshold voltage. This is big beta R. It's all off to one side. And then we make smaller beta R. It's going to go this way. We'll start going up and up and up. And finally, kind of asymptotically approaches this point, which is the ultimate smallest beta R. And it has to go through this transition to go into the active portion. What this is saying is that this will occur at a voltage which is VDD plus a threshold, which is above VDD. So it's only an asymptotic picture. There's VDD over here, there's VDD plus V threshold, and this is approaching this point of leaking out as a perfectly flat characteristic. So these are all saturation characteristics. Smaller beta R been moving up this way, and the last leaking out point, where it's almost 0, just touches the transition curve at the input voltage of VDD plus V threshold. This may be a little crowded. I'm just going to move this over here. There's one threshold voltage above VDD is what it tends to look like. And it's this point here. And of course, it's going to go nowhere after that. These are all pretty lousy. Nothing. We're not doing any transition at all. It's a lousy curve. Somehow we want it to go in the middle, but all right. So let's see if we can get the active part. So this is when we transition here and we start to go down. What is that curve? We discovered this was a parabola. And then how about the other one? So this is the active. So we set up our equation, load line. set it equal to the full-blown nonlinear equation in the active section. So that would be beta n times VGS minus V threshold times VDS minus VDS squared over 2. And we would have to rearrange this equation to make it look like a quadratic. And when we do that, we get VDD minus VDS. We put together all the VDS terms, there's one here, and there's one there. So it's a linear thing, is 1 plus beta in R times VGS minus V threshold. And then the leftover one is this guy here, which is times beta, and that cross multiplied by R, which is why the R shows up over here. So this is plus R beta n VDS squared, which is the quadratic term. 2 equals 0. Once again, we have here's the ax squared plus bx plus c. We can solve closed form, which is why we like to do this problem. It's a nice closed form. And the a is equal to beta n r over 2. The b is minus all this stuff in bracket, 1 plus r beta n times VGS minus V threshold. And c is equal to plus VD. And rearranging all that equation, we would then get VDS, solving the quadratic equation, is this messy b, okay, and minus all that, so this would be 1 plus r beta n times VDS minus V threshold over r beta n plus or minus square root of same guy, 1 plus r beta n times VGS minus V threshold, all squared, close the bracket, minus 2 times the guy here, which is beta n r times VD. And the 2's all work themselves out. Divided by beta n r. Is in here. The question is, what sign do we use? Which one? We're trying to come down from this point. So the only way it's going to come down with increasing VGS is if we have this thing over here pulling down on it. So this has to be a minus sign as you pull it down. Okay. And so we now have an expression for this. This is Bn. This is Bn. And here's the out. Okay. We're just bringing it all down to summary. This is the part of the curve down here. This is this curve here, transitioning from this point forward. And it's V out equals all this stuff, which is 1 plus r beta n times V in now. That's V threshold, just get it all through V in divided by r beta n. And we're doing a minus sign now, square root of 1 plus r beta n times V in, that's V threshold squared, minus 2 beta n r v, all divided by beta n r. That's the equation for this curve here. And you go back and verify what happens when we hit on this particular curve here. What does that get? When we turn out we get the same equations we got before. In fact, that might be kind of a homework problem, just to kind of get you used to using some of the equations. Let's see what else we have. All right, so that is what happens if we use just a resistive pull-up. And the problems we got into were if we made a big, it did kind of get sharpened down here, but it happened too much to the left, the 3 feet threshold. BDD would be someplace out here, or to BDD and simple threshold way off to the right. And it's just hugging too far to the left to give us a decent noise margin on the bottom end. You have to be centered below the threshold, and the only noise you can tolerate would be maybe half of this width here, half threshold voltage is the noise margin. It's not very good. What we want is something that's more out in the middle or noise. So how do we fix this? You know, our problem is that this resistor is just a straight line. The resistor that was pointed up is giving us this stupid straight line, and we're sliding along that line. Wouldn't it be great if we could somehow change the slope of this line selectively so that at the beginning we would hang around this higher level? This is more ideal. It would be nice if instead of rolling off right here, we could somehow push the nose of this thing up or somehow get it to just hang around up here. So this is the VTC, you know. And instead of rolling it off quadratically, wouldn't it be nice if we could sort of make it like this? Just stay up there and then start rolling off at BDD over here. Well, one possible way of doing that is to have a nonlinear resistor. That gets us into the idea of NMOS. Here's our characteristics. And our problem was before we had a fixed slope for our load resistor. And as soon as we break out a cutoff, we're going to go sliding along that curve, and it turns out it rolls off like this. Wouldn't it be nice if we could kind of turn it up this way, turn the load line up this way, so it would hang around BDD for a longer period? So here's one resistor, here's another resistor. Would it be nice if it went up like this? But then it would never get to the other end. But if we could, for a little while, make it go up like this, and then go over like this, bend over. And the thing that looks like the most is a reverse plot of the very characteristic that we're plotting for the nonlinear device. We suggest that we use a transistor instead of a resistor in the pull-up path that has this kind of characteristics. It's like a real steep resistor at the beginning, so we hang around up here, but then rolls over, then plummets off the cliff, and then goes down. And that's this cliff, actually. This is called NMOS, and it's a half step towards CMOS, which would be the next step. The same argument that we would have for CMOS, whether we want to start with a high slope in the load line, and we want it to roll off. So I'm going to start with NMOS because for a couple of reasons. One, it kind of gets the idea of a nonlinear load line under our belt. Second thing is that there's certain 3-5 semiconductor groups, gallium arsenide, and phosphide, and so forth, where we need to use the same kind of device, namely an in-channel device, to get the best performance, because generally for those technologies, the electron mobility is much higher than it is for holes. And we prefer to have in-channel everything, because it runs faster. So NMOS is useful to begin to see how having this load line vary and make it into a nonlinear load line is helpful, and it already is captured a bit in doing it. But it's a half step towards what we would do full CMOS. And if we can't do full CMOS, it provides the hint of what it is that the CMOS is trying to do. We have other solutions that might do the same thing. Now, this idea is to make a fixed characteristic. And how do I get a nonlinear load line like this, which, however, somehow is fixed, just sort of sticks up like this? One possibility is to somehow put a fixed voltage onto another transistor so that it is biased up here someplace, another NFET. And but that requires additional voltages. So another idea is the so-called depletion implant. Which will kind of put the thing a little bit more towards being already past inversion. Sort of this half on. We're going to make a leaky transistor is what it amounts to. And so what we do is we do an extra doping step under the, before we put the gate on to do the self-aligned source and drain implantation. We do an extra doping which kind of causes these types of transistors to be sort of on most of the time. They leak big time. This is called depletion mode load. And we're going to denote this kind of transistor by putting a thick thing here where the gate usually is. And it denotes that we did an extra implant to make this thing sort of want to be on. So it looks more like a resistor and not so much a switch. Otherwise, it looks about the same. And this is called a N-type depletion mode load. And it's a nonlinear resistor which will already be on, you know, even though we're varying the other device. So here's our other transistor, the conventional one, with all the steps that I talked about before. But what am I going to put here? It turns out with this extra doping, you can actually wrap this around here like that. So there's actually no voltage on the gate. It's already on. It leaks. And it looks like a nonlinear resistor that's just leaking. So this is what becomes of the resistor that we had there earlier. This is our VGS. That's for the N-type device. This is the VGS. That's for the N-type device. The IDS is going to flow through the two of them. This is the resistor. And this is with the nonlinear load up here. This is called NMOS. It needs an extra processing step on these N channel to make it look sort of like it's on most of the time. And that's basically what I'm going to cover for today. I have to get to a telephone and talk to IBM. I'm going to shut the class down early today. Is there any questions about what we covered? A lot of the